Today I'm considering reactions of alkenes. This is the first in a series of videos. In this particular video I am going to focus on the fundamentals, and we're also going to consider Markownikoff's rule. Now, alkenes react by electrophilic addition. This is the name of the reaction mechanism, and it simply describes the first step in this mechanism, because all reactions happen via a series of steps. Before we go any further, I think it's important to remind ourselves of the nature of a carbon-carbon double bond. So when carbon reacts, it's able to change the shape and energy of its atomic orbitals. It can mix them up to form what we call hybrid orbitals. Let's have a look at how that operates in ethene, or alkenes in general. So carbon has got 6 electrons. We've got our 1s2, our 2s2, and our 2p2 electrons. The 1s electrons are not involved in bonding. It's the 2s and the 2p that we are interested in. So let's have a look at those on an energy level diagram. We've got our 2s and our 2p, and of course there are 3 2p orbitals. We've got the px, the py, and the pz. So 2s, 2p, and in the carbon atom our electrons are arranged like so. But when we're forming a carbon-carbon double bond, what ethene does, or the carbon atoms in ethene do, is that they hybridize or mix up the 2s with the 2px and the 2py orbitals to make 3 identical sp2 hybrid orbitals, and it places 3 electrons into those orbitals. These 3 sp2 hybrid orbitals are essentially the orbitals that are responsible for the single bonds. So one of them is going to be used to make that carbon-hydrogen bond. The second one is going to make that carbon-hydrogen bond, and the third one is going to make a carbon-carbon bond. These are known as sigma bonds. So half of our carbon-carbon double bond is a sigma bond. The other half of our carbon-carbon double bond is a pi bond, and that comes from the merging of the unused 2pz orbitals on each carbon atom. So if we were to have a look at that, so we've got carbon with its sigma bonds in each case, and then each carbon atom has got 2p orbitals. Remember, those are the general shape of 2p orbitals. And each carbon has got 1 electron, so it's going to put in between them a pair of electrons, and that pair of electrons is going to exist in an area of electron density that sits above and below the carbon-hydrogen skeleton. Now, the electrons in this pi bond, firstly, pi bonds are much weaker than sigma bonds, and these electrons can be used to attack electrophiles and to make new bonds, and that is how alkenes are able to react. A good way to think about it is that the electrons in the pi bond can be redeployed. And if I bring an electrophile into close proximity with my double bond, the pi electrons are able to come out and attack that electrophile and ultimately form a bond with it. Now, what is an electrophile? Well, as we can see here, it is a positively charged ion, or it might be a neutral molecule. If that is the case, then one of the atoms in that neutral molecule is going to be delta positive. Either way, our electrophile is able to accept a pair of electrons, i.e. the pi electrons, pair of electrons, and it's going to use them to form a new covalent bond. The reactivity of an alkene depends on its stability, and there are a couple of factors that determine the stability of an alkene. Firstly, we know that E isomers are more stable than Z isomers. So that is my E isomer. My Z isomer, of course, has got my two R groups. In this case, they're just methyl groups on the same side of the double bond. So that is my Z isomer. These groups are actually quite bulky, and they tend to cause a little friction between each other when they are in close proximity. So that makes the molecule a little less stable. This is known as steric hindrance in posh language. The other thing we know is that the more substituted an alkene is, the more stable it is. So, for example, an alkene which has got 4 different, in fact, they don't need for different, but 4 different alkyl groups attached to the carbon atoms is going to be more stable than one that, say, only has 3. So remember, R stands for alkyl. An alkyl group could be methyl, ethyl, propyl, butyl, and so on. So the more stable the alkene is, the more reactive it's going to be. Let's take a look at the reaction between propene and hydrogen bromide. HBr can behave as an electrophile because it has a delta positive hydrogen, and it has a delta positive hydrogen because hydrogen is bonded to the considerably more electronegative bromine atom. When it comes into close proximity with the electrons in the pi bond, these electrons attack the delta positive hydrogen, and this in turn causes bromine to leave, breaking the HBr bond. Now this is an example of heterolytic fission because both the electrons in the hydrogen-bromine bond go to the bromine, to the more electronegative element. Note also the use of arrows. They're double-headed arrows because we're showing the movement of pairs of electrons, and I'm very, very specific about where my arrows start. So they're going from the pi bond and it's attacking the hydrogen. The electrons in the bond are moving from the bond onto the bromine atom. So be very, very careful about the drawing of your arrows. This step leads us to an intermediate carbocation. So we have carbons. The sigma bond between the carbons stays intact. The carbon-hydrogen bonds are unaffected by this. And the new hydrogen is going to add to that carbon, which leaves the other carbon with a methyl group, the hydrogen it already had, and a positive charge because it's now missing its pi electrons. This is an excellent opportunity for the bromide ion to behave as a nucleophile and to seek out that positive charge, use one of its lone pairs of electrons to make a covalent bond to the carbon atom that's electron deficient. The result is we end up with this molecule here. So we've got our 3 hydrogens, our bromine, and our methyl group. Note the change in geometry as well around the carbon atoms. We started off with a bond angle of around about 120 degrees, a planar molecule, and we end up with a tetrahedral shape, around about 109.5 degrees for our bond angle there. Now I want to look at this first step in a little bit more detail. It's very interesting to note that, let's start again. So here is my propene and my HBr, and my pi electrons coming out to attack the delta positive hydrogen atom and the delta negative bromine, leaving with both the electrons from the hydrogen bromide bond. From there we form, as I said, a carbocation intermediate. Now, theoretically, we've got two possibilities. We have the one that we looked at a second ago. So the hydrogen adds to the end carbon. But we've also got the possibility, theoretically, that the hydrogen could have added to our first carbon of the double bond, leaving the carbocation positive charge on the end carbon. Now, this never happens. The hydrogen always bonds to the carbon atom with the fewest alkyl groups, and whatever it was bonded to, in this case the bromide or the bromine, always ends up bonded to the carbon with the most alkyl groups. So this carbon here has an alkyl group, this carbon here has no alkyl groups previously attached to it. This is known as Markownikoff's rule. Markownikoff is regularly spelt in two different ways. So Markownikoff, or sometimes with the double F, Markownikoff rule. Let me repeat that. Markownikoff rule tells us that the hydrogen atom always bonds to the carbon with the fewest alkyl groups, and the X, whatever that X was, i.e. the delta negative part of our little molecule, always bonds to the carbon with the most alkyl groups. Now, rules that are learnt with no prior understanding always get forgotten in the heat of the moment in the exam. So let's see if we can understand why Markownikoff's rule is the way that it is. The reason is that this carbocation is more stable, so it's more likely to form. It's a bit of a chicken and egg scenario that happens quite a lot in chemistry. Why is it more stable? Well, if I were to redraw this ion, so I've got H, I've got a methyl group, positive charge, and this CH3 is really just another methyl group. Alkyl groups show a positive inductive effect, which means that they push electron density from the sigma bond towards the carbon atom, so they help to stabilise the positive charge. When we look at our second theoretical possibility for the carbocation, this carbon here is only going to be stabilised by one alkyl group. This is essentially CH3CH2. It's an ethyl group bonded to the carbon, and then the carbon's got two hydrogens. Hydrogen atoms do not show a positive inductive effect, so the ethyl group would be helping to stabilise it, which is only one group compared to our favoured carbocation, more stable because we've got two alkyl groups bonded to that positively charged carbon, helping to stabilise the carbocation. So more stable because we've got two alkyl groups stabilising the carbocation through a positive inductive effect. And if you want to know more about inductive effects, then there is a video in this playlist just for you. Finally, writing an overall equation to represent this reaction. We would have ethene, so we've got CH3, CH, CH2, going to form our product, CH3, CHBr, CH3. And then we write the conditions on the arrow. So, concentrated HBr, aqueous in solution and at room temperature. Now, this is a very important point. There is always more than one way to carry out a reaction, which means that the exact reaction conditions will be different from one textbook to the next, from one syllabus to the next. You need to know all the reaction conditions for every reaction. So start building huge mind maps, start building flashcards, and use the reaction conditions that are actually stated in your textbook and your syllabus. Okay, this is really, really important. Don't leave this to the last minute. 2 weeks before your exam is not the time to start learning reaction conditions for all the reactions. Start learning them now, because if you do it in a kind of drop by drop way, it's going to be far, far less painful. If this has been useful, hit the subscribe button, the effortless way to support your studies. And by clicking the link in the blurb below, it will take you straight to the Crunch Chemistry School, where you'll find all the resources you need to get that A-star grade at A-level. Together we can do this.